Hello and welcome back to this course covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing protocol-independent routing, where we'll review Junos routing features independent of dynamic protocols. In this lesson, we'll be exploring Layer 3 load balancing in Junos. Load balancing can allow for greater utilization of network resources, though must be configured with care to ensure a negative user experience is not the result. Unlike Layer 2 load balancing using link aggregation groups and LACP, Layer 3 load balancing doesn't require any cooperation or configuration with the next hops to implement. Where both sides of an LACP lag link must be configured to exchange LACP control frames, Layer 3 load balancing does not require any such cooperation between upstream and downstream devices. Let's dive in and see how Layer 3 load balancing can be configured, applied, and monitored in Junos. Junos is able to load balance traffic across multiple links through the mechanism of equal cost multipathing, sometimes abbreviated as ECMP. ECMP will balance traffic over multiple paths of the same metric or cost. It's important to note that this can be configured on a per packet or per flow basis. To determine flows, Layer 3 and Layer 4 information is inspected to build a flow table so that packets which are related to one another as being in the same data stream may be routed over the same links. By default, Junos does not perform ECMP. If equal cost paths are available, Junos will simply select one to use as the next hop installed for that destination, and all packets destined to that route will be forwarded to the selected next hop. Let's dig a little more into the differences between per packet and per flow load balancing behavior. In the example on the right, we see the effects of a per packet load balancing distribution. The different colors represent packets in a related data stream. In this case, we see that the two streams have packets which are both traversing different paths in the destination. If perhaps there is sufficiently high latency through one of the paths, the packets may arrive out of order. Although this is not necessarily a problem for asynchronous protocols, as most application traffic is, real-time protocols typically have a very large problem with out-of-order packets. Being that real-time applications, such as voice and video, are commonplace on most networks, a per-flow load balancing scheme is much more appropriate and will help ensure packets do not arrive at the destination out of order. On the left, we can see the packets of each flow are traversing the same links. This is achieved in the packet forwarding engine. So, let's take a look at how to accomplish this. The load balancing action is configured through the use of a routing policy. As such, the same flexibility that comes with routing policy definition may be used for specifying which traffic should be load balanced. Load balancing specification occurs at the policy control point when the routes within the routing table are evaluated for entry into the forwarding table. Although the action specified for the policy is load balance per packet, the default behavior of Junos when it comes to load balancing is identical to what other vendors call per flow load balancing. This is because by default, Junos will hash Layer 3 data within the transit traffic to determine which path should be taken. The configuration of the policy action to load balance traffic is only the first step. The policy must then be applied for it to take effect. Load balancing is enabled by matching route information in a policy and applying the load balance per packet action. This policy is then applied as an export policy at the Edit Routing Options Forwarding Table configuration hierarchy as shown here. In this case, we applied the policy Load Balance All, which was simply a policy that matched all routes and enabled load balancing on them. This will allow all routes which have equal cost paths towards the destination to be load balanced between those next hops. Had we applied the load balance sum policy, only a subset of the destination prefixes would be load balanced. The idea that this is an export policy may feel somewhat counterintuitive, though this diagram shows why this is the case. We're setting an export policy on the forwarding table within the routing engine, which will apply load balancing for destinations in the forwarding table programmed into the PFE. Thus, the export policy is used because the information is being exported from the forwarding table contained in the RE to the forwarding table contained in the PFE. When the policy is applied, no change in the routing table will be seen. The routing table will already contain the multiple equal cost paths towards the destination, which will not change. The only change observed will be to the forwarding table. As such, if we want to observe these changes, we need to look to the forwarding table to investigate. In this example output of the show route forwarding table command, we can see that there's a single destination prefix which has multiple next hops available. The 10.11.12.0/24 prefix shown here shows two valid next hops, 192.168.2.1 and 192.168.2.2. You may notice that the type of these next hops are UCST, or unicast, and hold. The currently active next hop at the time of the command being entered is the unicast type, whereas the other is not in use for that packet being transmitted. Because of this, you may see any of your next hops showing in a hold at any time. I appreciate you working with me to learn how to configure, apply, and monitor load balancing in Junos. I hope that this lesson has been informative for you, and I would like to thank you for viewing.